Hello and welcome to Canfield Power Systems Technical Webinar Series. This is part one of a three-part series this summer. As a reminder, all attendees are in mute or listen-only mode. If you have a question during the presentation, please type it in the question pane in the GoToWebinar panel. Throughout the presentation, we'll have experts monitoring those questions. We'll compile those at the end and address them, and some of them will be answered online. As I said, during the end, we'll have about 15 minutes for Q&A. And also the webinar is being recorded, and we will share that once the presentation is completed. Thank you. Subject of today's webinar is the top 4 enemies of gas turbine performance. My name is Jim Benson, Principal Engineer with Canfield. Tom Carter from our sales staff will be my co-presenter, along with Sophie Belanger, our Global Product Manager, who will be handling the questions for us. Our mission here at Canfield Power Systems is to provide turbo machinery with reliable, intelligent air solutions for the maximum predictability and minimum complexity. The agenda today will go through a brief introduction. We're going to talk about gas turbine degradation, and once we introduce those 4 enemies, we're going to discuss how to deal with them, how to mitigate those with filtration. And then Tom Carter is going to talk about taking the idea of the mitigation and analyzing it using a life cycle cost technique. And then we'll have time for question and answers at the end. So gas turbines operate in a number of different markets and in areas, applications, including power generation, which tend to be the larger size turbines where we're generating electricity either through perhaps a state-owned utility or an independent power producer. Also, within the power generation, we consider the turbine manufacturers, the OEMs. The other area of application for gas turbine within the industrial area would be oil and gas, and that would include offshore applications, FPSOs, upstream, midstream, downstream, refineries, natural gas pipeline compressor stations, those types of things. Those tend to be smaller turbines, but tend to have a higher duty cycle, and tend to run more on a 24/7 basis. And the third area of application is what we call process industries. So gas production is perhaps the largest segment of that group, and that would include air separation, those types of things. Would also include coke oven and gas for steel production, kind of specialty type of applications. Introducing our top 4 enemies. They are in kind of order of the machine: erosion of the compressor section. Also within the compressor section, there's the risk of cold corrosion, of fouling of the compressor section. Within the combustion and power turbine section, the enemies would be plugging of the cooling passages and then hot end corrosion. So what's the impact of these enemies on your operation? Well, they address 3 primary areas. First of all, it reduces the reliability of your operation. And by reliability, that's anything that's going to result in loss of operation, perhaps doing a forced shutdown due to a high pressure drop of your inlet system, or worst case would be a damaged turbine. The second impact would be related to availability of your machine. And that's where you have unplanned or additional maintenance. Perhaps it's due to unscheduled offline compressor washes. And the third impact would be related to performance losses, a reduction in power and increase in fuel. There's a common factor to these 4 enemies, and that is they're all caused by contaminants in the air, whether you call it dirt, dust, pollution, particles, salt, grit, whatever you may call it. That's the common attack, the common factor for these 4 enemies. So before we get started, we just want to give a brief review. Within the filtration industry, we talk about those contaminants with respect to their particle size. A lot of people have the conception that your air filters are installed to deal with large particles, the particles you can see. Perhaps it's dust kicked up from a road when a vehicle goes by, or perhaps it's a sandstorm. In reality, those are relatively large particles from our perspective. The slide here is to give some context to the particle size that we measure and we prevent from going into your turbine. Within the filtration industry, we talk about particles with respect to their size in microns. I suspect the audience knows that a micron is 1/1,000,000th of a meter, 1,000th of a millimeter. But the slide here is to give it some relative size basis. So as shown, your average human hair is someplace on the order of 50 to 80 microns. The particles that we're dealing with that are cause for at least 3 of the 4 enemies are 10 microns and smaller. So we're talking about particles that are 1/10 the size of a human hair. Depending how good your eyes are, you can see down to about 30 microns. So again, it's the small particles. When we get into submicron particles of things like diesel soot, they're on the order of 4/10 of a micron. Tobacco smoke on the order of 3/10 of a micron. So it's particulate in the air you can't see. When I'm giving this talk in a conference room, for example, and I have a projector going in a dark room, if you stand at a right angle to that light beam from the projector, you can see those white flecks floating around the air, or sometimes you'll see a sunbeam coming through a window and you'll see those flecks in the air. Those are the dust particles that are ambient in the air at all times that your turbine is ingesting. So again, just to give it, when we talk about performance and the enemies here, remember we're talking about very, very small particulate in the air. Our first enemy we're going to discuss today is erosion of the compressor section. Erosion is simply the abrasive removal of material of the machine. Compressors, turbines run at very high speeds, very high tip speeds. So even a small particle, when it's impacted, there's a lot of energy, a lot of inertia related to that interaction between a small hard particle impacting a metal blade going at a high speed. So it's essentially sandblasting the blade. It's changing the airfoil. It's affecting the surface finish, making it rougher. It may damage the leading edge. All those will reduce the aerodynamic performance of the machine, which will result in loss of compressor efficiency, which equates immediately to loss of gas turbine performance. It's important to note that this is a non-recoverable degradation. It does permanent damage to your machine. It requires either a major repair or a replacement of the component. In the figure on the lower right, you can see both a new and an eroded compressor component, where you'll see at the root of the blade on the left, the material has been eroded from that. That's an example of erosion. Typically, the particle size that will cause erosion is 5 micron particles and greater. So it could be all the way up to beach sand, or it could be particulate you can't see, but over time it will attack the materials. Enemy number 2 is corrosion. I tend to think of corrosion as chemical erosion. Again, a non-recoverable degradation, require replacement or major repairs. Corrosion can happen throughout the machine. Hot end corrosion is the most common. However, if you're in a coastal or offshore application, we have seen cases of the compressor section where we've had salt and water being ingested to attack those materials also. For this discussion today, we're going to talk about briefly one slide on the causes of hot end corrosion. If anyone's interested, we have subject matter experts who can go into much more depth and detail regarding the various types of hot end corrosion. There are 4 elements to hot end corrosion. First and foremost is temperature, the heat up to 1,000 degrees Celsius. And then we have two other components required, and that is sulfur from the fuel and salt from the air. Those three things combine to make sulfuric acid families of gases that will attack and eventually damage the highly sophisticated metals of the power section and of the combustion liners. Our third enemy to review today, and again, this is kind of a very quick overview of what the potential problems and challenges are in the field. And later on this summer, with the other two webinars coming up, we'll talk more about, this will be a building block for those webinars that we're going to be introducing both in July and August. Cooling passage plugging is a condition where modern turbines in the compressor section, in the power section today, again, are running at very high temperatures and have required a cooling air, a boundary layer, if you will, of cool air to go over that blade to increase its life and maximize its performance. That cooling air is taken from the compressor section. And as the illustration shows, both hot and cold air coming through, again, to provide that sheath of cool air to extend its life. If the air in the compressor section is dirty, small particulate will be transported through that labyrinth of patterns, and over time, those small particles on the order of 2 microns or smaller will start to stick together, and over time, it could block those small cooling holes, those pinholes. If those get blocked, you're no longer cooling the blade, and you'll result in issues of thermal creep, which means the blade is getting larger in diameter, and you're running the risk of having a clash between the blade tip and the casing, causing a catastrophic failure, or the risk of thermal fatigue and having a particle break, also again resulting in a catastrophic failure. Our fourth enemy today is fouling of the compressor section. And this is the case where, as opposed to erosion, where we're taking material away, we're actually adding material to the compressor section. Small particulate are adhering to the components over time and slowly building up. That's going to alter the shape of the compressor airfoils, increase the surface roughness, which is going to increase the airflow drag, all resulting in the compressor not moving as much air, not moving the air as effectively as it's designed to do. Particulate size we're interested in fouling is 2 microns, often one micron or less. And local environment is an important factor. In addition to the size of the particulate, the nature of the particle is also important, such as whether it's a diesel particulate or sticky hydrocarbon. The total impact is loss of compressor performance and loss of output. And the next slide shows an example of a couple of different turbines that were operating side by side in a very aggressive environment, where over about a 3-month period, with the standard filtration system they had installed, they were losing up to 10% of their power loss. Very dirty site, very unacceptable performance. A improved filtration was added to that site, where the reduction in power loss was now 3% versus 10%, still relatively high over a short amount of time. And this test was done several years ago, and with modern technology, we can even reduce that 3% loss to something more in the order of 1% loss or better. And the slides on the right-hand side may be a little difficult to see in the presentation, but you can see the cleanliness between the 10% power loss and 3% power loss of the first stages of the compressor section. So throughout the webinar, we're going to be presenting some polling questions. So our first polling question today is, which of these 4 enemies are your enemies? So for the users and operators in the group, we're very interested to see what your feedback on those may be. So please take a moment and answer those questions for us. And whether it's erosion, corrosion, fouling, or cooling us. At this point, I think I'll invite my co-presenter, Tom, just to make sure he's online and do a quick sound check.
Yes, good morning.
And we're getting a lot of responses coming in, so that's positive. Thank you for all participating. Tom, do you have a prediction as to which one of these is going to be the most interesting or the most common problem for our audience?
Yeah, I would expect to see fouling be the predominant enemy here, just because anymore with basic filtration, you can protect against erosion pretty good, and there's a lot of other steps you can do in addition to the filters to protect against corrosion. So if I was wagering, I probably would wager on fouling being the winner here.
Okay. So the results are in, and looking at the results, people have more than one problem, because obviously we're getting a percentages that are more than 100. So some of the audience have clicked more than one thing, but kind of as you thought, Tom, fouling is an issue, but the rest of the other three enemies are equally distributed. So across the board, these are common issues with respect to the audience we have today. So, so now that we've introduced what those enemies are, we're going to spend just a few minutes talking about how to deal with them and how to mitigate them. So again, the common cause is particulate in the air, and the solution is proper air inlet filtration. And it's most important to note that by proper inlet filtration, that doesn't mean one solution for every application around the world. It's our philosophy is to make sure that we tailor the solution to optimize for your environment in your application. And our third webinar at the end of or middle of August, excuse me, is going to address that specifically. So first of all, erosion. As I said in the introductory slide, from a filtration standpoint, these are big particles, greater than 5 microns. And our perspective, and anybody in the industry, they're fairly easy to deal with. That commodity level filter can handle 5 or 10 micron particulate quite effectively. When gas turbines were introduced, industrialized perhaps 40 years ago, maybe a little bit more, this was the primary concern of the engine, was to keep it from erosion. As turbines became more sophisticated, then we ran into the needs to deal with corrosion, plugging in the cooling passages, and fouling. It's important to note that if you are having erosion, and according to the poll, 59% of our audience did, and you do have a decent inlet filter system installed, you need to do an inspection of your inlet system to verify you do not have system bypass. You don't have leaks in the system, for example. Perhaps it's a defective flex joint, or perhaps a gasket that was installed 30 years ago that hasn't been maintained. So again, if you have erosion issues in your system, do an inspection on it. To mitigate corrosion, there are 3 things that can be done. And as I said, the engine manufacturers have recognized corrosion for some time, and they've addressed that by adding corrosive resistant coatings to the blade. Those have made a vast improvement to the problem, but it's not a 100% solution. Over time, those coatings will also wear off, and it's still important to deal with the causes of corrosion, and that would be sulfur from the fuel, and in our case, deal with salts and moisture from the inlet system through proper filtration. And by proper filtration, it needs to be effective on the salts, on those small salt particles and moisture coming in. With respect to the particulate, we mean a HEPA level efficiency or better. 85% on small particles, 0.2 micron or smaller. In some cases, you need to be even higher than that. And most importantly, we need hydrophobic filters, which has 2 components to it. One is a water-resistant media, so that any water, any salt water that may be present in your application doesn't migrate through the air filter media. And also, if we stop that water, we need a filter design that's robust that will drain that water away so it doesn't create a short life or pressure drop problem. A quick note on salt is that salt's kind of an interesting contaminant or particulate, at least for the filter engineer. That is, it's not stable. It will change its size with respect to humidity. So if we have a submicron salt particle and humidity increases, the size of that salt particle will increase. Salt is hydroscopic. It'll has an affinity to water vapor, and it will grow a size. So from a filter standpoint, up to a given level, that's a good thing, because generally speaking, bigger particles are easier to stop and retain than smaller particles. However, there's a transition point around 70 or 80% humidity where that same salt particle will change its state. It will go from a solid particle to a droplet or to a liquid, and that term is called deliquescence. And when it turns to a liquid, that's where it becomes imperative that you have a hydrophobic filter, because now I'm not trying to stop, collect, and retain just a solid particulate. I need to deal with a droplet or a liquid. In some media, particularly older commodity level medias, are not very good at that. So we'll have a saline saltwater droplet percolating through the media that will now be ingested by your machine and challenging it with and become one of the enemies to create a corrosion issue. Plugging of the cooling passages fouling are mitigated in the same manner because it's the same size of particles that we're dealing with. Smaller than the erosion side, 2 microns and smaller, and certainly many studies have been done, many papers have been written by ASME and others, that even submicron particles over time will adhere to the blades and degrade the performance. It's very much environment dependent. We see a vast variation in environments across the world with respect to particle size and concentration. Our general solution is high submicron efficiency, HEPA class, and that could be done if it's a static barrier style system with multiple stages, or it could be done with improved efficiency on cartridge filters also. So there are 2 ways to mitigate fouling. One is to deal with the effect, which I suspect most of the audience already does, and that is to do a water wash of the compressor section, whether you do it on an online basis or an offline basis, or you deal with the cause, and that is to improve the filtration to mitigate or minimize the amount of small particulate being ingested. So that leads us to our next poll question, which is, how do you tackle these enemies? So do you tackle them with compressor washes, blade coating, cleaning the fuel, upgrading your filtration, or you're not sure? So if you take a minute to address those, that would be helpful. And I don't know, Tom, given the results of the first section where fouling was a little more prevalent, but the others were a serious issue, I'm curious to see what kind of results we get here also.
Yeah, it should be interesting. Hopefully everyone wants to look at filtration upgrades as their #1 priority, but I do think that technology has allowed itself with blade coatings and whatnot and fuel control to really give you a lot of options at the site to attack it from different angles. So I think the results will be very interesting.
Yeah. And we're getting good responses also. A lot of votes or opinions coming in. Thank you very much. And as you can see on your screen, the results are in kind of split, kind of a tie between filtration upgrades and compressor washes. I think, as I mentioned in the introduction slide a moment ago, compressor washes, I think, are fairly common, almost standard operating procedure. But upgrades are also becoming more impactful. There are some OEs that are specifying very high levels of filtration, and so that they can minimize the number of compressor washes for your site. Thank you for
Just a
answering that,
comment
everybody.
before we move on from that, Jim. I would wonder if it would be possible for folks that indicated compressor washings was something that they use to help mitigate that. If it'd be possible to get a quick chat message or something to identify if that's online or offline washes, if we could differentiate between the two.
Yeah, that'd be great if you're able to either put in the chat window or perhaps in the questions at the end, if those who answer compressor washing, just a brief note on number, if it's offline washes only or if it's online washes in addition. Thanks, Tom.
Sure.
Okay. We talked about how to mitigate ever so briefly as an introduction of the four enemies. It's important to note that along with increasing your filtration, we also need to consider pressure drop. I think the audience is aware that pressure drop is resistance to airflow. It's the energy loss measured in pascals or inches of water, depending where in the world you are today. Things that add pressure drop to your inlet system, first and foremost, are your air filters, but also you have a parasitic pressure drop in your inlet system that's there all the time, even if you were to run it, which we don't recommend without filters. And that's the ducting, the turns, elbows, and getting the air from ambient to the inlet of your machine. Silencers and perhaps inlet cooling all add pressure drop to your inlet system. And it's important to monitor that throughout your life to get the best performance of your machine. Simply put, the higher the inlet pressure drop or DP, the compressor needs to work harder to pull that air in to get enough air to drive the combustion and drive the power turbine. So the harder the compressor needs to work, the lower the output. The rule of thumb is about 2/3 of the gross horsepower of a gas turbine is needed to go back into the machine, go back in the compressor section to drive it, to actually get enough air to make it work. When we speak about pressure drop from an inlet system, we're interested in the average operating pressure drop over its life, not just the initial DP of the filter, not just the number that's shown in a test report or a spec sheet, but how is it going to behave over the 4, 8, 10, 12, 16,000 hours it may be running. So this graph here is given a typical representation of the impact of pressure drop on both relative power and relative heat rate. The typical rule of thumb would have it for every 250 Pascal or every 1 inch of water, there is between 1/4 and 1/2% reduction in power. And as the red line shows, there's also a corresponding increase in heat rate. While that fraction of a percent of power may not seem like a lot, depending on your application, your operation, say 0.5% of power times your power output times your operating hours per year times the value of your output, that can add up to be a significant economic input if you can save even 100 Pascals or 1/2 inch of water. It could make a big difference to your economics over time. That's something Tom is going to introduce in a moment when we discuss our life cycle cost thinking. So this brings us to our third polling question, which is, when or why do you change your filters? And that is, do you change it on pressure drop, on a planned outage, based on a turbine manufacturer recommendation, an OEM recommendation, or a matter of economic optimization, or you're not sure? So if you take a moment to respond to those, that would be good. And Tom, you want to comment on the concept of economic optimization?
Sure. It's probably a relatively new term to a lot of our listeners this morning, but there's tools that have been developed recently that allow you to really monitor, and not just monitor, but predict when's going to be the optimum time to change filters from a financial standpoint. And it's going to be really interesting to see if we have any folks with us today that have adopted that process and go from there, as opposed to the historically most common way of doing it of planned outage.
Okay. Yeah, absolutely. It's, as you said, it's kind of a newer concept. And there are at least a few people who clicked that response as I see the results coming in. And thank you for participating in the poll. And as you can see the results here, I'm a little surprised, Tom. 55% of the people are changing on pressure drop. My experience has been a lot of folks, at least in North America, tend to be changing on a planned outage. Sometimes they correspond with the pressure drop, but oftentimes they don't. Interesting.
That's a little surprising, but it's very encouraging because it's part of the story that we like to tell, you know, as far as maximizing the life of filters and protecting your engine at the same time. So that's encouraging.
Yep, absolutely. Thank you all for responding. So, and to try to bring all these concepts together in a simple slide showing a pyramid or a triangle. With respect to filter performance, there are three key parameters we look at, and those three key parameters relate directly to the enemies I've just discussed. So when we're measuring filter performance, we're looking at the pressure drop of the filter, we're looking at its dust loading or filter life, which is a proxy for the service life you're going to experience in the field. And lastly, filter efficiency. That is, how effective is it at stopping those particulates coming in that may be erosion or salt or submicron particles driving fouling and cooling passage plugging. So it is an engineering trade-off, and what we try to do is optimize those with our with any filter recommendation we make. So with that, I'm going to let Tom take over the discussion and talk about life cycle cost analysis and trying to put some economics to those three portions of the triangle. Tom?
Thank you, Jim, and thank you for all the good information you shared, and most especially thanks to everyone that has taken time out of your day or evening to join us and hear a little bit of the Camfield story. I'm going to give you a brief overview now of a tool that we really lean on and are very proud of. It gives our customers a lot of good information. It's called life cycle cost analysis. And this is a tool that Camfield developed a number of years ago and has refined it continuously. And it allows us to compare several different filter options under site-specific conditions. And we do it by evaluating the effects of pressure drop and compressor fouling for that particular environment. And it allows us to show it to you in a dollar value or monetary value standpoint of what the cost effects can be of specific choices you make for filters. So what is it? Like I said, it puts a monetary value. So it's a financial tool where we consider all cost, procurement and operational, and we try to identify the key cost drivers for your site. And there's a lot of inputs, and some of them are constants that really don't change much, but there's a lot of variables too that are going to be specific to every site we visit and try to do solutions for. One of them, and first and foremost, is the gas turbine model, and not just the make and model, but also, you know, what version of that model are you running or upgrade package. The environment is very important. It's the one unique factor to every site. Cost of fuel can be a very big factor, and of course the value of the output you're making your product, which is power. And you know, we mentioned earlier that we take into consideration procurement and operational cost. Procurement cost can be some or all of the things you see listed on the screen. It may be an inlet system cost. You may be in a situation where you're buying a new filter house or modifying or retrofitting your filter house to accept different type of filters. And if that's the case, we need to factor in that cost. Replacement filter cost is the most common cost everybody associates with an inlet system, you know, and we kind of get hung up sometimes on what a filter costs. But what we like to show you is that it's just one of many costs you need to consider, and sometimes it's a very minor cost for the overall picture. And of course, when you're dealing with filters, you have to pay to have someone change them out and to dispose of them. And operational costs are a little more in detail, and you define the operational cost by looking at GT performance reduction. You know, if you have a high pressure drop, if you have a high fouling incident, it's going to reduce your performance of your GT, and there's a value to that. Compressor washing sometimes it's a big deal for a site, sometimes it's not. But when you consider the cost for compressor washing, the cost of the materials to do the wash is kind of minor. But if you have to come down for an unplanned stop, or you have to schedule time to come offline to do a wash, that can be very expensive. And if that's part of your conditions, we need to make sure to factor that in. Downtime opportunity is another thing that we like to talk about, because, you know, engine availability may or may not be a big factor for you. But as I said earlier, we consider pressure drop as being one of the major factors that we want to evaluate when we do a life cycle cost analysis. So there's two different types of pressure drop. One is constant DP, which is the inlet system itself. That's the resistance across your filter house, your duct work, maybe a silencer, an elbow. But those things are constant. They're always there. They're never going to change. Then you have dynamic DP, and that's related to the filters you're running themselves. And every choice of filters that you make is going to have a different initial pressure drop and an additional a different running or average pressure drop. And these are things you can control and you should look at and evaluate. And when we talk about pressure drop on the system and we're modeling filter life, which is an important segment of the LCC, we do it on average DP. You know, what's it going to average over the life of the runtime? And in order to do that, we have to consider the media design and the type of media, the environment. And I've referred to environment several times, and basically what we're talking about is the amount of particulate and the size of it that you're looking at for your particular site. And then we like to compare filter lab and filter test data and pull all that together to be able to create a good model for you. Fouling is a big factor for a lot of sites. It's something that Jim talked about in detail. It's a very common problem that can happen, and it's something that you can very easily control with the right filter packages, but you have to find that optimum fit or that sweet spot. And in order to model the fouling effects, we use filter test data. We use the environmental data that we mentioned already. We glean information from theoretical engine data. You know, different engine types will react differently as heat rates increase and things of that nature. And we try to pull that into our equations. And we support all of that with actual field testing and case studies that we've done in the past. So we do all of these things I mentioned in the previous slides just so we can come up and show you a nice chart. And this is a chart that was derived several years ago from an exercise we did with LCC to create a cost ratio model for a customer. And what you see are 5 different filter solutions. On the far left-hand side is the solution or the package the site was currently using, which was a high velocity, mid-grade efficiency filter package. And for the high velocity, I mean, as you can see, it's 4,500 CFM per filter. The final filter was an F7, which is right in the middle of the efficiency range. We started evaluating ways we could improve upon that for them. And the first thing we did, we went to a medium velocity system at 3,000 CFM per filter and gave you a little bit higher efficiency filter in F9. And it looked pretty good. We brought the effects from fouling down significantly. The pressure drop effects were still pretty high, but it was an improvement over what they were doing. Then we looked at 3 options using a more conventional airflow per filter at 2,500 CFM, which is kind of an accepted industry standard. And we started using EPA class or very high efficient filters as the final filter to do an evaluation. And the green bar really came down and pretty much disappeared after we did that. So with all of that said, the takeaway from this slide that I want you to see is that, yeah, the optimum solution for this site was a very high efficient filter, but it wasn't the maximum efficient filter that was available. And when we're driving toward trying to find the optimum selection for you by using a tool such as this, we find out frequently that it's not always the highest efficiency filter that's going to be the best selection for your site. This slide shows another example of the results that come from an LCC exercise. This is a site we did 4 solutions. One of them, the one on the far left, solution 1, is what they were currently using. And as you can see, they were paying a very big penalty for the effects of fouling. And we looked at different ways of improving that. And the solution on the far right-hand side really brought down that operational cost. And the number you see there under solution 1, 2, 3, and 4 is the estimated cost to operate this system over a 5-year period. So in this example, we could take them from being around $26 million to a little over $2 million to operate that system. And when you see the data here, this is the data behind the bar graph. And what's interesting to note, and we'll kind of compare solution 1 with solution 4, since that's the one we're recommending, we're asking the site to invest a good bit more in their filter cost over the 5-year period. And we're also asking them to accept a higher penalty and pressure drop over that time frame. But we're doing that so that we can almost remove the effects of fouling from their system. And we can't say we remove fouling. I don't think you can ever remove it all the way, but we greatly mitigated it from seeing a $21 million cost penalty for excessive fouling down to $86,000. In the lower half of this slide, you see some more data that we use. Something that has just come up in recent versions of the LCC, we're able to calculate the CO2 output, the intensity, and the tax rate for a given site. And in today's world and moving forward, this is going to be more and more important to be able to calculate and consider. And lastly, at the bottom, we always like to talk about estimated filter life, what we think is going to be the filter life for different solutions and different stages of filters. And on this slide, you can see that on the solution that they're running, we estimate they can probably run about 5 years or 40,000 hours with their pre-filter, where we're only going to get about 28,000, which is still pretty significant, but it's really reduced from what they were getting. So we're, being very upfront saying we're going to improve your system, but you're going to have a little bit of be willing to change some filters and invest a little bit more in filters to run much more efficiently. And that was a very brief overview of the LCC, but hopefully it gave you a snapshot enough to show you that it is a really valuable tool. And anyone that would like more information on it, reach out to your local Camfield office, and we'll be glad to do some detailed analysis with you. And with that, I'm going to kick it back to Jim Benson. Thank you.
Okay. Thanks, Tom. Thanks, Roll. At this point in time, we're going to, Sophie, I'm going to turn to you to see what we have for questions and open those up on my other page here and see we have some questions to address.
Yeah. Quick question, Jim. We had question about when we look at air inlet treatment, like inlet heating or inlet cooling. Does that have an effect on the air filters themselves? And what should be design consideration for the filters if you have air inlet treatment on your inlet? Okay,
fair enough. So depending on which treatment it is, let's take cooling first. I mean, you're cooling the air inlet to increase the performance of your machine because you're cooling the air, you're increasing the mass flow into the turbine. Higher mass flow means more energy, higher output from the machine. The only impact on that is there's a slight increase in the airflow per filter. But generally that's something that's accounted for. You may see a slight increase in pressure drop across the filters when the cooling system's on because you're increasing the mass flow of the turbine, but the volumetric airflow is staying the same because the turbine is a fixed sweep. So cooling has minimum impact on a filter system, particularly on systems that were designed that way. Retrofit systems, there's a potential if they put the cooling upstream of the filter, if there's the risk of having any condensate or high humidity now challenging the filter, that's something to consider. But those would be in more of a retrofit or aftermarket type application. Inlet heating, kind of similar answer, minimum effect on the filters themselves. You're changing the flow rate ever so slightly. And with inlet heating, for those that are upstream of the filters, the idea for a barrier system is you want to provide heat to prevent snow and ice from building up on the filter to create a pressure drop issue. So hopefully that's a quick answer to probably a 30-minute discussion.
Thank you, Jim. Another quick question here for Tom. First, there was a question about the availability of the LCC tool. Can people find it online? And if not, how can they get an analysis from the LCC tool?
Okay, yeah, it's not available online. It's something that you have to reach out to your local Canfield office and have someone from the sales team get with you and perform the LCC with you. We're glad to do it, at your office, or these days, I guess we would do it, over online together. But yeah, we have to actually operate the program with you and the tool with you, but then we'll give you the results.
Sounds good. Thank you.
Yep. Yeah, I think that's fair. I mean, it is, as Tom indicated, there are a number of inputs to it, and we want to make sure we get those inputs correctly modeled. And it does have some proprietary features to the model also that we're pretty proud of.
Perfect. One other question here was the customer has a site where the OEM is recommending to change the filter after the final filter after 2 years of operation. According to their evaluation, pressure drop is still pretty low. What other inspection should be done to the filter to warranty that they're still doing their job in terms of physical inspection or lab testing?
Okay, I guess I can take that one. So in addition to pressure drop, as filters get older, what we like to do is have filters returned to our engineering test lab for evaluation. We'll validate the pressure drop that's being reported by the site, and 99% of the time that always agrees. And then we'll measure its efficiency to validate it's still performing at the level it needs to, from that perspective of keeping the particulate out. And then it's looking at things, condition of the media, conditions of the gaskets. Sometimes it's more common on peaker plants with cartridge filters, for example, where they're installed a long time, that we'll recommend replacing the filter due to the condition of the filter itself. Gaskets may be degrading or the media is degrading. But again, we look at the overall conditions of gaskets, and conditions of the media, including where appropriate, test the media strength.
Thank you, Jim. We had another question about coalescing performance and hydrophobicity performance. Should filter be coalescing or hydrophobic? And what do we recommend? Should they be fully hydrophobic, based, I'm assuming, on what filter stage they are placed at?
Okay, so yeah, as you kind of hinted at, Sophie, this is the answer where customers hate engineers, and it's going to be, it depends. So coalescing and hydrophobic are two different properties. And in a coastal application, for example, my recommendation, you would do both. So a coalescing filter is going to take small droplets in the air, make them bigger, and separate them out before they were to get to a final stage filter. And in a coastal environment, we would like to have, think of a coalescer as a pre-filter for droplets, pre-filter for moisture, if you will. And so that we're not overburdening the hydrophobic media downstream. So we're going to take out the bigger droplets, the smaller droplets, make them bigger, and then deal with the moisture itself at the final stage to keep it from entering the turbine.
Thank you. And as a follow-up on that, on corrosion and salt, I have a question here saying that we often read about E12 as a recommended filtration efficiency to remove salt completely. What is our experience on final filtration grade? What is sufficient, and what other characteristics are important to remove the salt?
Yeah, certainly the E12 recommendation has become much more common. It's been more reasonable in the past, let's say 10 years, due to enhancements in the filtration industry. We're able to get acceptable performance. If your environment, and again, we'll go back to the comments Tom made, we look at the environment. The environment warrants E12, particularly in a coastal application. We fully agree that that's the right answer. And there are a couple of different filtration technologies to get you to E12. Some may be hydrophobic and some may not. There are membrane filters out there that have a degree of hydrophobic and high efficiency that may be appropriate for a coastal application. If you're an inland application, we can achieve hydrophobic, or excuse me, E12 efficiencies if you have a lot of submicron with perhaps glass fiber media where the hydrophobic and the expense of a membrane filter is not required. But again, we like to look at each situation again, and I think in the subsequent the next webinar, they'll probably address a little bit about what an E12 filter means, but it's a very high efficiency filter. It's 99.95% or 99.5% on particulate less than 0.2 of a micron.
I have a good question here that we often get. I think it would be nice to touch. What is our recommendation on washing and reusing filter? Can that help prolong life of the filter?
Tom,
No.
Would you like to comment on that one first?
Very quick. I'll give you a very quick no on that one, Sophie. We do not recommend washing and reusing filters for a variety of reasons. If maybe a follow-up conversation with the person that asked the question would be warranted to explain that in more detail, but just the short answer is it is not recommended.
All right.
Yeah, and I'll add just briefly in that, I saw a case several years ago where somebody attempted to do it in a very crude manner, where they were washing them literally in a 55-gallon oil drum and dipping them, and they turned out actually washing dirty filters with dirty water and actually put more contaminant on the clean air side of the filter than they removed from the other side and created a risk issue to the turbine. So yeah, I agree with Tom. These filters, both ours and our competitors, are not recommended for washing. You don't get any value out of doing that, and a great risk of doing more harm than good.
Speaking of environment and system design, there's a question here about how to prevent ice buildup on the filter and also the impact of velocity in that case specifically.
Sophie, could you repeat the last part, please?
Yes, the impact of filter velocity on ice formation. Do we have any recommendation, and what other method could be used to prevent ice buildup on the filters?
Yeah, ice is a challenging problem. And part of it depends whether it's naturally occurring or if it's from the site, such as from a cooling tower drift. The answer to the second part of the question is the lower velocity, the better. You can deal with it more effectively. There are several mitigating opportunities for that, including inlet heating, whether it's hot air mixed upstream of the filters. If the ice buildup is not severe, several sites have had success with infrared lamps, but again, the velocities need to be low there. So that becomes kind of a very situational thing, and maybe we can deal with that individual more specifically offline. But it is a challenge, but we do have ideas and solutions to deal with those.
Thank you. We don't have much time left, maybe one or two questions. There was something we haven't touched much is pulsing. So there was a comment about, I guess, cleaning the filter through pulsing, and what would be the recommendation there in terms of pulse schedule as well. Well, let's start with this one. So where do we pulsing, and at what recovery do we consider there's no more recovery and we should change the filter?
A kind of a complex question, and very much environment dependent. Generally, the original system is going to have a high point and a low set point on pressure drop, where it'll start pulsing at let's say 700 pascals, and it'll clean down to probably say 400 pascals. When it cleans down to that, it'll stop pulsing. Many sites will do that in a preventative manner, and maybe pulse on a weekly basis if they know if they haven't. That helps them to maintain their filters at the best possible pressure drop. And my other recommendation when to pulse is if you have a weather forecast that you're going to run into a weather event, whether it's sandstorm or even a snowstorm, I recommend turning the pulse system on and running it continually throughout the event. If the pulse system cannot, through pulsing through several cycles of the filter house, and it cannot recover its pressure drop, then it's time to consider replacing those filters. Tom,
And just yeah, I have a side note to that. I think that offline pulsing can be very valuable, especially in high dust concentration areas. If you can program your pulse controller to run 1 or 2 cycles with the system offline, it can be very effective to avoid re-entrainment of dust.
good point.
Yeah. I think that makes about the time we had here for Q&As. Don't worry if we haven't had a chance to answer your question. We will answer them by email privately following this webinar. So we'll stay online for a few more minutes too. If you have more questions, please type them in the question box. We will take the time to answer that right after. And thank you, Jim and Tom, for this excellent webinar as well. I'll pass the screen to you again.
Okay. Well, again, thank you for everyone for your attendance. I wish you a good morning, good afternoon, or good evening, depending where around the globe you may be. And as a reminder, our upcoming webinars for July 21st relates to the value rating, a way to establish and select your air filters. And in August, we'll be talking about selecting the right filters to improve your efficiency, reliability, and availability of your machine. And those will be done by both Canfield engineers and some outside consultants helping us with that one. So once again, thank you, and goodbye.
Goodbye, everyone.